So let's start with actually going back and forth between regular equations and log and semi-log equations. So you're really only ever going to be faced with two different types of equations. Either you're going to have an exponential function, which is going to be y equal to something times some base to the x power. So I've written as y equals k times a to the x. Or you're going to have a power function. You're going to have y equal to some constant times x to a power. Excuse me. In either case, if you're trying to see what the transformation looks like, you're going to take the log of both sides. And it is log base 10. So for all of these log, semi-log stuff, we're always talking log base 10. So if I take the log of both sides here, then I'm just going to use my log rules to break this apart. So the right-hand side, log of k times a to the x becomes log of k plus log of a to the x. And then this, you can bring the power down, and that becomes log of k plus x times log of a. And notice that in this side here, the x is still kind of normal, right? We don't have log of x, we just have x. So this is why this one becomes a linear graph on a semi-log graph, because one of the variables changes and one of them is still essentially what it was to begin with. So we replace log of y with y, right? Essentially we're graphing log of y on the vertical axis and regular x on the x-axis. That's why it's semi-log or half log or log linear. And so this is what it's always going to look like. You're going to end up with some capital Y equal to your slope, and your slope's going to be log of your base. That's always what's going to happen. So whatever this a here is, your slope is always going to be log of a. And whatever this constant up front here is, your y-intercept is going to be log of that value there. So your d is log of k. On the other hand, if you start with a power function and go through the same steps, you'll get a slightly different result. We're still going to start by taking the log of both sides, right? That's always kind of, if we're starting with just a regular function, we're trying to transform it, you're taking the log of both sides. Now, I should say, if you're given data to work with, this isn't exactly always what we do, but if you're given an equation, this is what we do. So if you have like data points you have to graph, there's kind of other things we have to work with. If you're just given something like this, then this is what we do. So then we're going to take the log of both sides. Again, we're going to break up this piece like we did before. So log of c times x to the p is log of c plus log of x to the p. And then this power can come down in front. So we get log of c plus p times log of x. And in this log looks terrible here. In this, we have a log of y and a log of x. So it's a log-log transformation, right? Both log of y is going to turn into capital Y, and log of x is going to turn into capital X. So here we end up with capital Y equals mx plus b, where the slope of it is this power of x. Right? So if you see a power function, you should end up getting that the power there is the slope of your linear line in the log-log graph, and that your vertical axis intercept is this log of your constant out in front. And this is always the way you would transform just an equation into a log linear or a log-log thing. And it's always going to be the case that exponential becomes linear on a semi-log graph, and the power function becomes linear on a log-log graph. Okay, so then we can also talk about working backwards. And that's a little bit slightly more complicated. So let's say that you were given kind of the setup that you had some data, you graphed it on a semi-log plot, and it was linear. Right? So someone told you you had data, you graphed it on the semi-log plot, and the best fit line was linear. And we want to know what the original function was. So here's what we do. If it's on a semi-log plot, we know we are plotting log of y versus regular x. So we start with log of y equals m times regular x plus b. Whereas if they said it was log-log, we would start with log of y equals m times log of x plus b. So there is a difference there. In this one, we start with this, and then we just solve for y. And in either case, you're going to solve for y by writing both sides as the exponent of the base 10. So I'm going to say that this is going to be 10 to the log of y equal to 10 to the mx. And then 10 to the log of y is just y. And I'm going to break this apart using my exponent rules. 10 to the mx plus b is 10 to the mx times 10 to the b. And then we typically rewrite the 10 to the mx part as 10 to the m to the x. And then usually most people like simplify 10 to the m. So if like, you know, if m is like 0.2, then you say, okay, 10 to the 0.2 is about 1.58. So you'd actually write that as 1.58 to the x. But more generally, it's just 10 to the whatever that slope is, power, and then raised to the x power, times 10 to the b is your constant for here. It's the same process here, just with a slightly different result. So here, if it's log, and so if we know it's linear on a log graph, then we know it's capital Y equals m times capital X plus b, where y is log of y and capital X is log of lowercase x. And then we do the same thing. We write both sides as powers of 10. We break up the right-hand side using our exponent rules. So we get 10 to the m log of x times 10 to the b. And the left side is just y. And then this 10 to the m times log of x is going to end up being x to the m. Because you can write it as 10 to the, you can write this m here as the power of x. So you can say it's 10 to the log of x to the m, and that's just x to the m. So we end up with 10 to the b times x to the m. So notice, if it's linear on a semi-log, our end result is an exponential function. You've got some constant times some number to the x power. Whereas if it's linear on a log, we end up with a power function. We get y equal to some constant times x to a power. So that should be a very firm connection in your mind, that log being linear corresponds to a power function and vice versa, and semi-log being linear corresponds to an exponential function and vice versa. Okay, that's what I had set up ahead of time to talk about that stuff. Let's see. I saw a question here that I wanted to address. Yeah, so let's look at, so someone asked about finding a function equation from the table to determine whether it's power or exponential. I find that to be really somewhat challenging. Let me go ahead and share my screen for just 1 second. And let me actually look back here real quick. Come on, share the screen. Actually do the thing.
I have a question.
Okay, go ahead.
So if we were given like 2 sets of points and asked to find, like based off the linear line, does that mean that we would be finding the original equation, or would we be finding the log or semi-log of that equation?
Actually, I'm assuming, I'm not sure who's talking, but I know someone asked that in the chat as well. And I was actually going to ask for more clarification on that question. So actually, let's go ahead and do that because I want to know how to do it as well. So do you have an example of a question that we can look at?
I think I can pull one up.
Okay. Why don't I go ahead and go through this while you do that, and then we'll get to that next. How about that?
Okay. Let me see if I can find one.
Sure. So I'm looking back at this data that I grabbed from chapter, I think 1.5, problems like 59 through 64. And I don't know what all the answers are, but we can definitely look at one of these examples and kind of see. So again, the question that was kind of in the chat that I saw, gosh, I always hate when I share my screen because I have to like find the chat again. It always wants to hide.
I have a quick question.
Sure.
Are you recording this?
Am I what?
Are you going to record this?
Oh, am I not recording it?
Oh,
It's
wait.
I'm recording.
I'm just blind. Never mind.
No, sorry. These meetings are always set to auto record the way I have it set up. So unless I accidentally turn off the recording, it should be recording. But yes, thank you. If you ever see that it's not recording, definitely let me know because I definitely mean to be recording it. So let's see. Yeah. So here we've got these various tables. And so again, the only way I really imagine how to do this is to graph all the things. So like if we look at, say, I want to look at, I think, now let's look at this one where we've got, let's look at these values here. So here are my X and Y values. And if we just graph those, we're going to see that it's not, well, I don't know. I mean, it could be linear, right? You never know. So again, the way to see how good the fit is to type this y sub 1, or to try to type it, y sub 1 tilde m x sub 1 tilde, or sorry, plus b. And then you look at the r value. And the r value there is pretty good, but maybe there's a higher one. So then we have to do x graphed versus log of y. And again, maybe there's an easier way to do all this. I don't know if there is, though. This seems to be the easiest way to me. So then I do the same thing. I do y sub 2 tilde m x sub 2. I can never find the thing, plus b. And the r value there is slightly smaller, actually. And so then we look at the log. So again, for here, right, I'm graphing the x values versus the log of y values. And now I'm going to do the log of x values versus the log of y values. And I don't actually know what the result is, although, oh yeah, so this one actually is linear, which is not particularly exciting, but it is good to know that sometimes your answers come out to be linear. So let's look at the final one. Let's do y sub 3 equal to.
I have a quick question.
Go ahead.
When we're looking at which one is the best fit for the graph, are we looking at the r squared or the r values?
Either one, actually, whichever one is close to 1. So the thing is here, if r squared is closer to 1, then the r value will be closer to plus or minus 1.
Okay.
So in each of these ones here, so in the first, r squared is bigger in the first one than it is in the second or the third. And the r value is closer to -1 than this value or this value. So you should be able to look at either value. It's just that if the slope is negative, r will be negative, whereas r squared will always be positive.
Okay.
Yeah, you're always looking for the one that's closest to 1 or -1 if you're looking at r, and it's negative. So yeah, this one not very exciting. It's just linear, so we're kind of done. So let's look at a different example. So I'm going to grab. Yeah, I don't think we did this one last time. I definitely don't think we did this one last time. How about this one? So I'm going to, let's see I wonder if I can be smart, if I can just copy this in there and paste it. Let's try. So if I copy this and paste it in here, no. Oh, no, it just wants to put at the bottom. Okay, let's close all the things. And there's too much stuff. Okay. And we want r sub 4, x sub 4. Okay, so there we go. Linear, the fit is r squared is 0.9879. So that's a pretty good fit, but I'm guessing one of the other ones might be better. So here is x versus log of y. Let's throw that on there. And then we will do again, the best fit. So we have to use the right subscripts. Should probably just figure out a way to copy and paste this every time. R value is r squared is a little bit smaller, so far the linear one is the better fit. Did I really pick 2 linear examples? It's really gonna be wonderful. Sometimes you pick the wrong examples. And let's check this one. So we've got y compared to, sorry, y sub 2 compared to m. Oh no, that's a better fit. So here our r squared value is 0.9999. That's like almost a perfect fit versus this one up here, which was 0.9879. So I'm going to turn the other ones off so we can actually see the one that is the one that's the best fit. So it's this one right here, and it's all very right. If you take log of both things, you're making both things much smaller, right? When you take log of something, you're making it a smaller value. So let's actually zoom in here. Ooh, let's okay, good job. So there are our data points, right? They're all very small numbers between like 1 and 2. So then what do we do, right? So we go back and we say, all right, I want to now use this result to write the equation of the original function it came from. Now, let me ask you guys, since we know a log-log transformation gave us a linear graph or a best fit linear line, what kind of original function is it going to come from? Is it going to come from an exponential function, or is it going to come from a power function?
Power?
Definitely power. So let's talk about how to. So here's the thing. Depending on what you want to do, you could totally just be like, well, I know that if it's log and it's power, I'm going to end up with this. So you could really, if you wanted to, say, okay, my final result is going to be y equals 10 to the negative 0.048425 times x to the 1.50923. Now, your teacher might want you to show the work. So if I were showing the work, I would start with, okay, I know that I did a log transformation. I'm going to stop sharing so you guys can actually see what I'm writing on the board. So I did a log transformation, and I got the best fit line, or the best fit being linear. I got the log transformation having the best linear fit. So I know I've got y equal to m, which I just said was 1.50923, x plus my b value, which is negative grossness 0.484255. And then you would just do the usual stuff. So you'd write log of y equals this times log of x plus that, which is still the same number. I guess I could write minus. And then you would raise both sides as powers of 10. In fact, we can kind of cheat and say like it's 10 to the this equals 10 to the that, right? If we're trying to save space. 10 to the log of y is just y. And this is going to be, I'm going to rewrite this as 10 to the 1.50923 times log of x times 10 to the negative 0.048255. And then this is going to become, some people, so I like to write this as the power here. Some people prefer to write it as 10 to the log of x to this power. It's the same result either way, because 10 to the log of x is just x. So you end up with x to the this. So you get y equal to x to the 1.50923 times 10 to the negative 0.048255. And I personally would choose to leave it like that because that feels more right to me. But we could also get the approximation. So we could say that 10 to the negative 0.048255 is about I'm going to cut it off at 3 decimals. It's about 0.895. So this is y is equal to 0.895 times x to the 1.50923. And that is the power function that fits the original data. So we don't need to, but you could go back and plot the original data again, the original y's and x's, and you can also graph that power function, and it would fit the data very nicely.
What were the givens here?
The givens, so I'm sorry, I apologize. So the given was this set of data right here. This 10, 20, 30, 40, 50, 60 for x. Oh, sorry, you can't see my screen, apologize. So I'm looking at problem 62 from section 1.5, but I will tell you, and I will show you that the given was this set of data here. The x's were 10 through 60, the y's were 29 through 430. So in fact, we can actually, since it's still there, we can turn this back on. I think if I zoom out a little, maybe. Yeah, so you have to zoom kind of way out to see that data. Right there it is. And if I delete this, if I actually graph that line right there, that power function, we see that, oh yeah, that power function exactly hits all those data points. So that's what's going on there. So this is how you would take data and figure out the original function that it came from. But I don't know a better way to do it. I personally find myself having to plot the x's versus y's, and then the x's versus log of y's, and then the log of x's versus log of y's, and seeing which of those has the best r squared value. And then picking that one for my m and my x, and then throwing it into this and finding the appropriate equation. Now, the thing you really have to remember after you do this is that if you did a log-log transformation, you have to throw it into this equation, where capital Y equals m times capital X plus b. But if it was a semi-log transformation, you have to throw it into the capital Y equals m times lowercase x plus b, where the capital is log of the lowercase. So that's a big important thing to remember, right? Are there any other questions about this problem? I think what I might do, because I have so much time, I do not have so much time. If I find myself with some extra time, I will try to make a video of me going through this type of problem and another one that is semi-log, just so it's there. I mean, also you can access this video after I post it, but I mean, I could make a dedicated video of just this type of problem if you want to see a couple more examples, like the other two problems we haven't done in the textbook. Anyway, I
have a question. So what if they only give us like, oh, y of 1 equals, or like at 0, y equals 60, and then they tell us it's on a straight line on a semi-log plot? Like, where do we go from there?
Sure. So that's kind of the, well, I feel like we need a little bit more information than that. So they're telling you this, right? They're telling you that you said when x is 0, y is 60.
Yeah. Oh, and then they give us like another point. They give us like the intercepts on y and the intercept on x.
Okay, so let me actually, I need to be clear about what we're actually trying to do here. So the question I need to know the answer to, I suppose, is this the original function that they're giving you points for, or is this the transform function? Like, are these points on the semi-log graph?
Let me see if I can find the problem, because I remember one. I'll go find it right now.
And I feel like someone else had this question as well. Yeah, Ali or Ali. Sorry, I'm never gonna remember what the right way to say your name is. I will try though. I promise I will try. Ali or Ali Mustafa, you had a similar question at the very beginning of the chat. Well, we can actually talk about either way. So I'm gonna make something up. Melody, if you have something else you want to come in with in a minute, you can. Let's say that we know that our semi-log graph goes through the following points. 0, 40, and 3, 20.
For the problems that I had, she gave us a table, and we were supposed to figure out if it was either semi-log or which one like fits better, semi-log or log-log.
That's kind of what we were just doing in the previous example. So for a question like this, okay, so this actually kind of, okay, now I know what we're doing. So the idea here is if you've only got 2 points and you know that this is like, so essentially we have this. And this is how I'm seeing it. So I've got my point 0, 40 here, and my point 320 over here. And there's my straight line on the log linear graph, right? So here's the thing. This point here isn't x, y, or at least not as we usually think of it. right? This is the point, right? Since it's semi-log, this is the point x capital Y, or if you prefer, x log of regular Y. And so is this. This is the point x log of regular Y. So the idea here is that if we want to capture the original exponential function, and we know it's exponential because it's linear on a semi-log graph, then what we're going to have to do is we're going to have to find the slope. And the way we're going to find the slope, yeah. So our slope here is not hard. It's just regular. It's going to be, 20 minus 40 over 3 minus 0, which is negative 20/3. Right? That is the slope of this line on the log linear graph. Now, so this is where you have to be super careful. This is where I think the challenging is. The challenge part is, it depends on how they're talking about these points, right? Are these points on the semi-log graph, or are these points on the original graph, right? That's kind of the difference here. And so we can talk about the other variety of that in just a second if you would like. In this case, we find the slope. We've got our y-intercept of 40, so it's not too terrible. So we know that we're starting with capital Y equals negative 20/3 times regular x plus b, where b value is 40. I get the impression that this is not the version that you guys might be concerned about, because this seems pretty straightforward, right? Okay, so I'm going to stop this question here because I think everyone could finish this one here, right? You could change y to log of y, and then you could do the whole thing where you solve for y. So let's go to a different version, which if someone has one, great. If someone doesn't, I know where to find one.
I kind of found one. So it's like express log 10 of a as a function of t, and then it's on a semi-log plot, and on the y-axis it gives like 10 to the third, like etc.
Okay.
And so it crosses at 10/3,
Yeah.
and then at the x-axis it crosses at, say, like 40.
Sure. Yes, I've seen this question. So here's the thing, right? Yeah, sure. I'm just using it. So the problem here is that the way this is set up is they're actually giving you, right? These are the actual y values, right? This is actually y equal to 1,000, not log of y. But we're plotting on a semi-log scale. So the idea here is that, when y equals 10 to the first, log of y equals log of 10, which is 1. And when y equals 10 squared, log of y equals 2. And when y equals 10 cubed, log of y equals 3. So that the log of y values are the things that are equally spaced apart. Right? Log of y is 1, log of y is 2, log of y is 3. Equal spacing. And so if I want to write, or a, I suppose we're using a here, not y. So if I want to write log base 10 of a as a function of t, well, here's what we're going to do. Log base 10 of a as a function of t is linear, right? I've got we'll work on it in a second. I've got my intercept here, I've got my intercept here. So I know that log base 10 of a is some linear function of t. Okay, now here's how we find the slope, and this is the part that's probably a little bit tricky. The way we're going to find the slope is going to be the difference in the y things over the difference in the x things. Or here's the difference in the log of a's over the difference in the log of, the difference in the t's. So it's going to be right, essentially your difference in your y's over your difference in your x's. Where I'm looking at this point here. So this point as t comma log of a, the t value is 0. The a value is 10 to the third. The log of a value is 3. This point here, the t value is 40, and this is where things are a little bit wonky. The a value is actually 1 because of how this graph thing works. I know it's kind of, so, right, this is log of 1, which is 0. So we end up getting negative 3 over 40 as our slope there. Which again makes sense, right? We're going over 40 and we're going down 1, 2, 3 marks. And so then we can say that log of A equals negative 3/40 t plus, and our B value is, what's our B value here?
3.
It is, right? Because again, if you're plugging in t equals 0, you should be getting A equal to 1,000, which means that log of A should be equal to 3. So this is our linear equation, assuming I haven't made some dumb mistake. And then you could, you could solve this for A, right? Or actually, no, this would actually answer the question they asked for, right? This is writing log of A as a function of t. If you wanted to write A as a function of t, you could go then write both sides as 10 to the and solve for the thing like we usually do. But I think we've done that enough times that I'm not going to work through it here. Yeah. So let me look at one more thing real quick here. Not you. Yeah. So
Wait, I have a question for that.
go ahead.
For like the side parts that you were getting for like the 10 to the 3, like were those given?
Yeah, these are totally given on the graph.
Oh, okay.
I only know that because I've looked at the thing. But yes, those are given. It's weird. So the hard thing about these log and semi-log plotting things is sometimes you're kind of transforming the y scale and sometimes you're not, depending on who's doing the graphing. So it can be very kind of confusing, I think. Let me do one more thing and then we will kind of move along. So let's say we know we have 2 points. So we have excuse me. Sorry. So we have the points that come from a power function. I feel like I'm writing this wrong. Sorry. Okay. Yeah. So, yeah. Let me see. So yeah, so we have 2 points that come from a power function, sorry. And those points, we know that the original points, not transformed, are, what do we got here? 3, 11.3 and 5, 32.2. I want to find the original function. And so I know that if I have a power function, that the log-log transformation should be linear. So I know that the log-log right? That's definitely the thing that is true about being a power function. So I want to find the original power function, and there might be a way to do this without actually doing what I'm about to do, but I think what I'm about to do gets more at the point of what you're trying to do, which is that I'm going to use these points to find the slope. Now here's the thing. These aren't the transform points, right? These, like if I was graphing the straight line, which is something like this, right? The points on my line aren't 311.3 and 532.3. It is the log of 3 and the log of 11.3. So this point here is log of 3, log of 11.3. And this point up here is log of 5, comma, log of 32.2.
Why would you do that since you already said it comes from a log-log graph, so wouldn't those just be the point?
Well, no, so I'm saying
took the log of them?
these are original points. So like my original graph, which I call the power function, right, looks something like, I don't know exactly what it looks like, but it's going to look something like this. And on the original graph, those points are 3, 11.3 and 5, 32.2. And there's probably actually a way just to find, like we could probably, I don't know, it might be kind of challenging actually. You might be able to find the power function just using this data, but I don't actually know how to do that right off the top of my head. But I do know how to find the slope of this line by doing the difference in the y's, log of 32.2 minus log of 11.3 over the difference in the x's, which is log of 5 minus log of 3.
I have a quick question.
Yeah.
So when we're finding the m value, or yeah, the m, I forgot what it's called, for there you go. For a semi-log, the top part is the one that's going to have the log, and then the bottom is the regular number, right? And then when it's log-log, they're both log, top and bottom?
Yeah, because for semi-log, the y's are changed into log of y's, but the x's remain the same. And for slope, it's always the change in the y thing over the change in the x thing. And yes, for log of logs, we're changing both of them, we're changing both of them. Yeah. And so then if we calculate this, we get approximately, what do we get here? We get approximately 2. I can actually calculate that. We do the log of, sorry, one sec. Where's my log button? Log of 32.2. And then divided by log of 5 minus log of 3. I should mention, yeah, I get 2, that you can simplify this bottom part as log of 5/3, and you can simplify this top part as log of 32.2 divided by 11.3, right? Using some of those logarithmic rules. And so then we can say, all right, we know that our equation, so this actually is a little extra tricky. So we know we've got y, log of y equal to 2 times log of x plus b. We don't know what b is yet. So you could find b by plugging in either one of these points, right? you could plug in, right? You could plug in 11.3 for y, and you could plug in 3 for x, and you can solve for b. So you're not given this point here, solving for that intercept value actually takes a little bit more work. So b would be equal to log of 11.3 minus log 2 log of 3. Which I would, if I was going to enter that into a calculator, here's what I'd actually do. I would simplify this first. I would write this as a log of 11.3 minus log of 3 to the second power. And then I write this as log of 11.3 divided by 9. Just because that's easier to enter. So doing that, I get 0.09, which is not the value I had over there. Oh well. Yeah, interesting. Did I make a mistake? I don't think so. I feel like I did though. That's weird. Anyway, it's not that important. It feels wrong though. I'm sorry. Sorry, when something feels wrong, it feels wrong. No. Sorry. Nope, that's it. Oh, yeah. I see the mistake I'm making. It is a dumb mistake. 0.098, which I'm going to round to 0.10. So then we could say, all right, we've got log of y equal to 2 log of x plus 0.10. And then we could do the normal transformation, right? Writing both of these as powers of 10 and solving for y. Which again, I'm not going to do because we've done it enough, I feel like. Okay.
I have a quick question.
Go ahead.
Do you have access to like our web work, homework? Because like some of the problems.
Sometimes I do. So currently, yes, I think I do. Yes.
All right. Because I have a question on one of them.
Sure. Which one?
Number 16.
Let's see if I can still access it. Of course you did that. Yeah, every time I log into it, after a little while, it just stops wanting for me to be logged into it.
Is that for homework too?
Oh yeah, someone was, yes,
Yeah.
I was definitely planning on talking about this question today for lots of people, because lots of people have asked me about this question. So I think that's definitely moving us in a good direction in that we're still talking about logarithmic stuff, but I think I'm gonna stop talking about log, semi-log. We've done quite a few examples. If you have more questions about log, semi-log, I do have office hours today from 11 to 12. You're welcome to come on by. But I do feel like there are lots of other things we should talk about as well. So let's talk about these log questions. Then I definitely want to do a half or exponential growth and decay examples with percentages, because someone was definitely asking about that. So let's look at a couple of these and then we'll move on. Let's say we've got something like the natural log of, so I'm looking at problem 16 from homework too, for those of you that have this. But here's what we're given. We're given something like natural log of a to the minus third over b squared c to the minus fourth. And we're also given over here that natural log of a is equal to 2, natural log of b is equal to 3, natural log of c is equal to 5. Now here's what you cannot do. You cannot just plug in something for a. Well, I'd say that's not entirely true. If you really wanted to, you could plug in that a is equal to e squared, which seems not like the point at all. But it is true, right? If log base e of a equals 2, it does mean that e to the second power is equal to a. So if you really wanted to plug in for a, b, and c right away, you could plug in e squared for a, and e cubed for b, and e to the fifth for c. But that is not the point at all. The point for all these problems is to use the rules of logarithms to break things up. So this breaks apart as the natural log of a to the minus third minus the natural log of b squared times c to the negative fourth. For a natural log of something to a power, you can bring that power down in front. So this is going to be negative 3 times natural log of a. Now, to be able to bring a power down, it has to be the power on the entire thing in the logarithm. And that, since we don't really have that here, what we can do instead is we can break apart this product. So I'm going to make a small mistake here, and I want you guys to catch it. I'm going to write this as minus natural log of b squared plus the natural log of c to the negative fourth. Okay, where is the mistake that I made?
Plus.
It is plus. The mistake, it's not so much the plus, although you're right. It's that I'm not distributing the minus sign there, right? Because it's minus all of this. And all of this is the natural log of b squared plus the natural log of c to the negative fourth. The thing I always remind myself when I'm breaking up a logarithm of a complicated fraction thing, all the things in the denominator should end up with negative signs in front of their logs, at least before we bring down the powers. So I have negative 3 natural log of a minus natural log of b squared minus natural log of c to the negative fourth. And then I can bring down those powers. So I get negative 3 natural log of a minus 2 natural log of b minus minus 4, so plus 4 natural log of c. And then after we've broken them all down so that each natural log is just a natural log of a single thing like a, b, or c, then we can say, oh, but natural log of a is equal to 2. This is negative 3 times 2. This is minus 2 times natural log of b, which is 3. And this is 4 times natural log of c, which is 4 times 5. So that's going to be negative 6 minus 6 plus 20. So negative 12 plus 20 is 8. So that's the idea here. The idea really is they're trying to get you to simplify these logarithms using the rules of logarithms. Now, what I want to warn you about is problems like C and D. There's some things you can't do. Like, let's look at problem C, or at least something very similar to problem C. I think all the problems are different for different people anyway. So, but I've got something like the natural log of a to the negative third times b to the negative fourth over the natural log of bc to the fifth. And now here's the thing that we cannot do. We cannot combine this top and bottom logarithm in any meaningful way. Right? You cannot write this as the natural log of this over this. You're stuck. The only way you can push logs together is if they're added or subtracted together. If logs are multiplied or divided, they're kind of stuck apart, which is okay, but it's just something to know. So I'm going to use the same product rule I did before. I'm going to say the top's going to be the natural log of a to the negative third plus the natural log of b to the negative fourth. And the bottom here, you could either distribute that power to each of those terms or just bring that power out in front. 5 times the natural log of b times c. And then on the top, you can bring the powers down. So I get negative 3 natural log of a minus 4 natural log of b. In the bottom, I get 5 times the natural log of bc is the natural log of b plus the natural log of c. But just like here, when I broke up this, I had to distribute the minus sign. Here, the 5 has to distribute to each of those. So it's really 5 times natural log of b plus natural log of c. And then we're at the place where we can plug things in, right? I've got natural log of a, that's just 2. So you get negative 3 times 2 minus 4 times natural log of b is 3 over 5 times natural log of b plus natural log of c is 3 plus 5. So that's the idea as to how these work. They're trying to get you to use your rules of logarithms to simplify these expressions.
If you were to distribute, like when you did the bottom, instead of like, if you were to distribute the 5 power to the b and c first, how would it change like the bottom? Like,
So in the end, it doesn't change it at all, right? It's still going to be the same. But here's how it would look. The bottom would look like the natural log of b to the 5th times c to the 5th. And then in the next step, you would have the bottom being the natural log of b to the 5th plus the natural log of c to the 5th. And then in the final step, you'd have 5 natural log of b plus 5 natural log of c, which is the same as here, right? It's just that here the 5 is distributed and here we haven't distributed it yet. But yeah, it ends up being the same.
So you know how when we started it was like the top divided by the bottom? Isn't there a rule where we can do like top minus bottom?
No, not in so here. So let me throw up the rules so you can see kind of what's going on. So here are the 3 rules for logarithms. The natural, I'm going to use log base whatever. Log base b of x times y is log base b of x plus log base b of y. So if they're added together, we can combine them as multiplication. Log base b of x divided by y is log base b of x minus log base b. And finally, log base b of x to a power is that power times log base b of x. Here are some things that do not simplify. Log base b of x divided by log base b of y. That's not entirely true, but this definitely doesn't simplify in the way that you think it would. And log base b of x times log base b of y. These are tricks. People trying to get you to make a mistake when they write that kind of thing.
Could you do this problem real quick? Because I'm having trouble with it.
Say that one more time.
Could you do this problem really quickly? Because I'm having problems with it.
Which problem?
It's it just kicked me out.
So we can come back to this in a minute, but I would really like to do an exponential decay problem. And there's actually 2 I want to do because there was a challenging one on the homework that I want to talk about. Before that, I want to talk about this one. So let's say we know that a radioactive substance decays by 30% in 8 days. What is the half-life? And then we could also ask, how long until 10% remains? For most of the time, for these exponential growth or decay problems, I find it very, very useful to make a little chart. Time versus the amount of stuff I have. Okay, so I know usually time equals 0 is the time I know something about. And then I'm also being told something about time being 8 days. The problem with this problem, although it's not really a problem once we get over it, is that we're not given any amounts, right? We're not actually told how much stuff we have. That's actually the best case scenario. I know it feels weird at first, but if you're not told how much stuff you have, that's actually really, really great because you can just make up any number you want. And I'm going to make up the number that I have 100 grams or pounds or whatever. I'm going to have 100 somethings. So time equals 0. I have 100 grams. I have 100%. And then 8 days later, how much do I have? Well, it says it decays by 30%. So how much do I have left? Oh, sorry, I'm not seeing all the chat because I'm scrolling all the way up. Yeah, exactly. I have 70% or 70 grams. Okay, so this is enough data to figure everything out, right? I have as much data as I need, basically, essentially 2 different spots to be able to figure out what the C and the K are in the model that I'm going to write. And then I know that I'm trying to figure out the half-life. So I'm asking what time is it when I have half as much stuff later? And then I'm also asking what time is it when I have 10% of what I started with? So those are the questions I'm trying to answer. So the way I'm going to solve this is by starting with the model y equals c e to the kt, or y equals m naught e to the kt, whatever letter you want to use there. But right off the bat, we know that c is going to be 100, right? Y is going to equal 100 e to the kt. Because if you plug in t equals 0, you're going to get 100 times e to the 0, which is just 100. So you'll get y equals 100, which is what we should get when you plug in t equals 0. So then we're going to use this piece of data. We're going to say that y is 70 when time is 8. I should try and not use up my black pencil. Right ones. So solving for k, I get, let's see. I'm sorry, I forgot to plug in the c, the 100 being c there. Sorry about that. So divide both sides by 100. You get 0.7 on the left equals e to the 8k. Take the natural log of both sides. The natural log of e to the 8k is just 8k. And then solve for k. So natural log of 0.7 divided by 8 equals k. So I'm going to write my model as y equal to 100 e to the natural log of 0.7 over 8 times t. There are other ways of writing this. I personally prefer to write it like this, but you could also write it as 100 times 0.7 to the t over 8. That would also work. All you're doing there is you're saying you've got e to the natural log of 0.7 to the t over 8. I don't like this personally. This feels foreign to me, but this might be the way you've always done it. So do whatever works. I think Karana has done it more like this. So yeah. Either way is fine though. All right, so now that we have our model, now we're trying to answer the questions. What's the half-life? So to find the half-life, we're going to set our model, which is 100 e to the natural log of 0.7 over 8 times t. We're going to set that equal to half the stuff we started with. And then solve for t. Divide both sides by 100. You e to the natural log of 0.7 over 8 times t. Well, 50 divided by 100 is not surprisingly 1/2. And then take the natural log of both sides. The natural log of e to the this is just the exponent. And then solve for t. So t is 8 times the natural log of 1/2 over the natural log of 0.7. So that's your half-life for this problem. It's not pretty. You could use the calculator to get an actual approximate value, but I would just leave it like this. And then I'm going to be lazy here to answer the other question. We would just, instead of plugging in 50 here, we'd plug in 10. And so then instead of getting 1/2, we'd get 1/10. And so this would be 1/10. And this would be 1/10. I know it's very, very lazy to do it this way. You should not do your homework this way if you're asked these 2 different questions, but it's right. It's the same process. Once you've got the model, if you're asked to figure out what time it is when you have some certain amount, you're just plugging that amount in for y and then solving for t. There is one kind of different flavor of this, which I think is a little bit challenging. And it's when you're doing some carbon dating stuff. So there was a question on the homework. I don't remember exactly what it was, but it was basically something like, I guess I could look if it was going to be, I forget what problem it was, but it was one of the earlier ones. I think it was like problem 3.
It was 3.
Yeah, I'm going to do some different numbers. So the half-life of carbon 14 is 5,730 years. And we find a piece of wood or something, I don't know, that has, let's say it has 30% as much carbon as it normally would. How old is it? And I will admit, solving these problems for me is always a bit of a challenge because it's always kind of, there's kind of 2 different ways you can do this. Here's where we're going to start then, right? We're going to start with, right, y equals c e to the k t. And make my little table. Now, here's the deal. Here's where we have to make a choice. And our choice does actually matter. We have to decide when we want time equals 0 to be. Do we want time equals 0 to be today when we found the piece of wood? Or do you want time equal to be however many years ago when the wood first existed, essentially first fell off the tree, I guess, right? When it started decaying. And that's really, I mean, either way will work, but it does make a difference as to how we solve this problem. So let's say time equals 0 is when we have 100% of the carbon. And then, well, see that I find it terrible to do it that way. I really don't like doing it that way. Time equals 0 is going to be when we have 30% of the carbon. And then we know that 5,730 years later, we would have half of that. And I know the numbers look a little wonky, but it's going to be okay. What we really kind of have to do is we kind of have to ignore the fact that we don't know what C is for a second and just figure out what the K value is. Now, there's a couple ways to find the K value. You might know a formula for half-life already. You might know that K is always equal to the natural log of 1/2 divided by the half-life. Or you might know that the half-life is always equal to the natural log of 1/2 divided by K. Those are things that are true. If you've taken chemistry, you probably have seen this fact before. So what I'm going to do is I'm going to use these 2 pieces of data. I know that at time equals, yeah, sure. So, yeah, this is where I have to justify to myself what I'm doing right here. So I'm essentially saying when time is 0, I've got 30%. So I'm essentially saying that my C here is 30%, which is kind of funky. Don't worry, it's going to work out all right. And then 5,730 years later, I'm going to have 15% of whatever I started with. Essentially, when you're plugging in that half-life time, 5,730 years, you should always end up with the equation 1/2 equals e to the k times 5,730. Because whenever you're setting this up, This number here should be half of whatever you're quote unquote starting with. So then taking the natural log of both sides, we get natural log of 1/2 equal to the natural log of e to the k times 5,730, which is just k times 5,730. And then finally, we're going to say that k equals the natural log of 1/2 over 5,730. Okay, so here's our model. Our model is y equal to 30% e to the k, which is natural log of 1/2 of 5,730 times t. Okay, so then what do? Well, we've got our model, and now we want to know what happens when y is 100%. So we're going to set our model equal to 100%. Now, what's going to happen is we're going to get a negative value for time, because we're essentially going back in time from time equals 0 to some negative value. That's okay. That's just how many years ago it was. So we're going to get e to the natural log of 1/2 over 5,730 t equal to 100 divided by 30 is 10/3. And the percents cancel, so you don't have to worry about the percentages anymore. And then take the natural log of both sides. So that on this side, you just get the exponent. And on this side, you're going to get 10/3. Sorry, the natural log of 10/3. And finally, solve for t. T is going to be 5,730 times the natural log of 10/3 divided by the natural log of 1/2. And using a calculator, we get, so also I should point out, just as a quick aside here, you can't simplify that, right? You can't divide those natural logs together, right? There isn't a rule for that. So we get 5,730 times the natural log of 10/3 divided by the natural log of 1/2. And I end up getting negative 9,952.8 years. So that means that the piece of wood that has decayed to having 30% of its original amount of carbon is 9,952 years old. That's what it means. There might be other ways of approaching this. There probably are other ways of approaching this. But to me, this is the way that I find easiest. Essentially, you're saying you're starting at time equals 0 with 30% of the stuff, and then you're saying, well, what time is it when I had 100% of the stuff? That's, to me, the way I like to imagine this one. All right, I know before I got started on all these exponential growth and decays, I believe Ali was asking a question. You're welcome to pose it if that was who was actually asking it. I didn't see who it was really.
Could you, for number 16, do number letter B?
We can certainly look at one similar to B, yes. So, okay. So there's a couple ways you can tackle. I mean, I'm going to say that a lot in this class probably. It is generally true that when you have a problem, there's often a couple ways you can tackle the problem, right? That's just going to be a truism. So we've got the natural log of b to the -6, c to the 4th a squared, and it's actually, sorry, it's the natural log of the square root of all that, which is going to be the natural log of b to the -6, c to the 4th a squared to the 1/2 power. And here there's two directions you can go. You can either go in the direction of saying, I'm going to bring down the 1/2. The other direction you can go is to distribute the power to each of these things. So if you've got a bunch of stuff multiplied together to a power, you're really just raising each thing to that power. So you can say that this is the natural log of b to the -6 to the 1/2 times c to the 4th to the 1/2 times a to the second to the 1/2. And either way is correct. If we go this way, then I'm going to break that up into 3 logarithms. So it's 1/2 times natural log of a to the negative 6 plus the natural log of c to the 4th plus the natural log of b squared. And then I can bring those powers down. So I get negative 6 natural log of a plus 4 natural log of c plus 2 natural log of b. And then if you wanted to, you can distribute the 1/2 and get negative 3 natural log of a plus 2 natural log of c plus 1 natural log of b. And then you could plug in natural log of a is 2, natural log of c is 5, natural log of b is 3. So you're getting negative 6 plus 10 plus 3, which is 7. Or you could do this. You could say, I'm going to look at this, and then this is going to be the natural log of b to the negative 3rd times c to the 2nd times a to the 1st, and then break that up as the natural log of b to the negative 3rd plus the natural log of c squared plus the natural log of a. And then that is exactly that, because you just bring down the powers. So either way you want to go is perfectly fine. You should be able to get to the same place. If any of these original powers had been odd, I might have opted more to go this way because, I mean, yeah, that's fine with odd powers. That doesn't really matter. Either way is good. Let's see. So, yeah. Let me look at one thing here. I know we're almost out of time. So my intention is on Thursday to start talking about sequences and limits of sequences. I feel like I probably shouldn't spend only 3 minutes talking about that. So instead, real quick here. Basic equations we should know for the chapter. That's a good question that I don't have a great answer to. Let me see here. Let's see. I feel like there's something else I should. No, not you. So here's a question on the homework that seems like it could be challenging. Maybe I'm wrong. You guys can tell me if this is not true. So they're giving you this function, clearly an exponential function, the way it's written, and the graph goes to the points what have I got here? Oh, they made this too easy. Zero, 5, and yeah, this is too easy. The reason this problem is too easy, in my opinion, is because they gave you one with a 0. If they give you one with a 0, it's super easy to find C, right? Let's make it harder. Sorry, let me cheat real quick. And this is something you run into on occasion, where your job is to figure out what this kind of exponential function is, where you don't actually have like the initial C value. So how am I going to figure out what C and A are? Well, I'm just going to plug in the points and see what I get. So I know that when I plug in 1 for X, I get 6 equal to C times A to the 1st. And I also know that when I plug in 3 for x, I get 24 for my function value. So I get 24 equals c times a to the third. So you always get 2 equations. Now, what could I do to these equations to figure out how could I combine these equations? Well, I could divide them. I could take this equation, 24 equal to c times a cubed, and divide it by 6 equal to c times a. I suppose what I'm really doing, although I'm being kind of lazy about it, is I'm actually solving each equation for c and then setting them equal to each other. So here you're going to get 4 equal to a squared. But really the work I probably should be showing is that here you're getting 6 over a equals c, and here you're getting 24 over a cubed equals c. And then you can set those equal to each other to get 6 over a equals 24 over a cubed. And if you if you multiply a cubed up there and divide 6 over there, you exactly get a squared equal to 4. It's just a lot faster to divide them by each other, which is totally legal, right? If you've got 2 things that are equal to each other, you can totally divide each side by the other side, and it's actually totally legit. So we get a equal to 2. Technically, the solutions are plus or minus 2, but when you have exponential functions, the base is typically not supposed to be negative. So we know that we're getting f of x equal to c times 2 to the x. And now that we know that a is 2, we can go back and solve for c, right? If a is 2, c has to be 3. If a is 2, oh yeah, c has to be 3. So our function is actually 3 times 2 to the x. This kind of, I know we're out of time, so I'll just point this out here. This kind of solving of an equation like this especially comes up when you've got like, and it's gonna sound kind of morbid, but typically there is usually a dead body problem in one of these chapters where they're like, they found a body at such and such time and it was this temperature. And then an hour later, it was this temperature. What time did the person die? Meaning what time was their temperature 98.6 degrees? And the idea is that essentially you've got 2 later data points, right? Where time is 1 and temperature is some number, and then time is 3 hours and temperature is some number. And then you basically go back and say, oh, I'm gonna go back and figure out what the function is and then plug in time equal to 0 to figure out what the original temperature is. So yeah, that's kind of some, and you do it by doing this thing where you first actually, right, you solve for like the exponent thing instead of the constant out in front first. All right, that is all I have to say today.